Okay, so next speaker, Alexis Bidot from Space Telescope, talking about enabling medium contrast spectroscopy with MIRI MRS.
Can you hear me all? It's okay? Okay, and where is... Okay, let's go. So I'm Alexis Bidot. I'm a postdoc at STScI, and today I will be presenting my work on direct spectroscopy with MIRI MRS for exoplanet imaging via forward modeling. So a short introduction of the MRS instrument. So it has two detectors simultaneously imaging one subband of each channel, of 4 channels. So you will get 3 observations to get the full coverage, the full wavelength coverage of the instrument. And that represents a span from 5 microns to 28 microns. But today I will drop the channel 4 for the longer wavelengths. The throughput is not good enough for our subject here. And so we have a medium resolution, about 4,000 to 1,500, and that's enable us to study molecular, to resolve molecular species in atmospheres. So not only being the favorite piece of engineering from Marshall, it's also enabled a ton of discoveries already. So we can quote a few of them. You already heard about some yesterday. We have detection of silicates in the brown dwarf. We have a new study around circumplanetary disk. And it's also thought that MIRI is the best instrument to study NH3, to constrain abundance of NH3. And even its isotopolog, 15NH3, that we have detected in a cool brown dwarf, and is thought as a formation tracer. So this discovery are the major discoveries were made on bright targets or long separated targets, but MIRI has a potential for medium contrast object as well. So JB talked a bit about molecular mapping. So what is going on here, we go through this kind of step. We take the 2D detector image, we run that through the JWST pipeline, we reconstruct a data cube, then we remove the starlight with a high-pass filter, and then we cross-correlate with our best guess or our best fit template or only molecules to make the companion appears in the CCF peak here. So I've been studying a not so famous system, which is HRI 799. You may have heard about it. MRS was maybe the only instrument not observing it yet. It has already been detected, the planets are already been detected in the mid-infrared with the coronagraphic mode. We can see the 4 planets at 10 microns, 11 microns, and then it gets blinded out by the inner disk luminosity. And it's very important for me because, as Jerry said, there is a lot of discoveries still to be made in those wavelengths yesterday, but it's also the deepest high contrast data set with MRS, with the longest exposure time to my best knowledge. And so that makes us wonder what contrast is achievable and what are the main limitations for now. So these are the first results that I got. So just taking the data cube straight out of the pipeline, cross-correlating with the best fit from Chuan and Rufio on planet B. And you can see that on band 1A, on band 1A, you get 3 detection of the planet. On band 2A, 2, and then only planet B remains in band 3A. But what is a bit shocking here is that the correlation for planet B in band 1A is very low, about 30%. And we are taking a best fit that matches very well near spec data, and we have like 50% overlap of the wavelength coverage here. So we should have a better correlation here. So what can be optimized? We saw also on previous data sets that high contrast was really challenging with direct output from the pipeline. We have beta peak B somewhere here, the tiny yellow dot, and GQB as well is pretty faint. So Martos et al. 2025 did a little experiment taking the high-pass filter data cube and trying to see what were the main limitations, what were representative of the main residual spectrum that you get inside. And so we identified that it was mainly dominated by residual fringing of MIRI-MRS. I'll get to that. And also the resampling noise. MRS suffers from undersampling. It relies on the 4-point Deezer strategy to recombine an equist sample data cube. And we get those sawteeth oscillation here, those wiggles that JB talked about just earlier. So what can be done about it? So my goal was to combine improved calibration and also forward modeling. You can see on the left plot here, the blue curves correspond to the fringing pattern observed on the peak of the PSF, and the orange one is what is applied by the calibration pipeline. So it's a very important effect, like it can affect up to 20% and more of the continuum for a point source. And the behavior of the fringing is not the same for an extended source and point sources. That's why we have a bad correction here. And for all the reasons JB told us about applying the forward modeling to get rid of the wiggles, etc. So thank you, Jason, for introducing Fabry-Perot effects. So here it's not coming from dichroids, but the detector in itself. And the fringing depends on the incident light. And so the illumination pattern is different for every Deezer, and we should get caution about this. Gassman et al. In 2023 suggests that we should take a look at A stars with the same Deezering pattern, with the same offset of the star, and run a Gaussian filter to estimate the fake continuum to see the oscillation of the fringes around that, mapping that, and use that finally as a flat fringe. So that works well. About 1% of fringe remains. I tried also to directly feed the fringe on the data itself. It's work in progress. It's working kind of well for channel 1, channel 2, but channel 3 has more complicated systematic, and I will just focus on Gassman technique to remove them. No. We have identified some other issue, dark subtraction, stray light removal, flat field issue. There is fringing, there is a lot of systematic added by this step, so we just decided to get rid of them in the pipeline. Forward modeling, so yeah, the first row is the actual scheme of the full forward modeling, but as JB told us, we can reconstruct a cube, but beforehand removing the star continuum. And that's what I'm going to show here. So these are the new correlation maps. We have a really good detection in a good improvement in channel 1, about 80% of correlation with the planet B best fit, so that's really great. And then it gets fainter for channel 2, and channel 3, it gets somewhat brighter. So yeah, I didn't really know what was going on, so I tried to take a look directly at the spectrum. So this is for planet B at the first band. So you see a very good correlation. The template is in black and the extracted spectrum is in blue. So quite happy with this reduction. But then going to channel 2B, we see a lot of systematics here, a lot of wiggles that should not come from the fringing because we have mitigated them. I think the correlation, the 30% correlation comes from the short wavelengths here, or we can see some features there. And so, no? Oh, there's something missing. Okay, never mind. My best guess is that there is an uncorrected stray light in the instruments causing not fringing transmitters, but emission lines. This is not very well known in MIRI-MRS. It's called the zipper effect, and you can see that it has those little blobs here are about the same luminosity of the speckle, and I know that they cross the companion B traces. So that might explain that we are not having a good extraction here. And for channel 3, finally, we see that it's more noisy than what we have with channel 1, but we're getting this kind of features there. Maybe the photometry is not perfect as for now, but it's quite interesting that we can get a better extraction for now. So a few takeaway messages. Please don't use the full pipeline to do high contrast imaging or high contrast spectroscopy with MRS. Try to get a reference featureless star that enables you to get a better sense of the fringing with the same Deezer pattern. So same Deezer pattern, but also with the same offset of the star in the Deezers. That's very important for the pattern fringes. As seen with NIRSpec, it has really helped the detection and spectral extraction working directly in the 2D images. I think that the zipper effect is the main limitation here for channel 2, so that's work ongoing. But I worked also on other data sets, for example, Epsilon in D, AB, and the star is not in the field of view. We don't have that scalar light, and we kind of get a better spectrum. So that's maybe one solution here if you have a prior on your companion position. And now the code is fully implemented on GitHub, on Brett's repo, and the tutorials are coming next. Thank you all, and take any questions.
So thanks for all the warnings. University of Hawaii, Eric Gaidos. Do you have any information yet on whether the scattered light is pointing or time variable? Have you been able to look into?
I'm sorry, the scatter light, what?
Have you seen if the zipper effect is pointing or time variable? If it's scattered light, then is it coming from off-axis sources, or is it?
Well, it's not very well understood by the MIRI team, so I don't have maybe more information, more personal information, but I can see that it's moving in the field depending on the Deezer, and when the star is offsetted of the field of view, it does not appear, so that's all I know.
Hi, Alexis. Great talk. Aniket Sanghi from Caltech. So we saw examples of fringing in both JSON stock at RF 35,000 and for MRS at moderate spectral resolutions. In both cases, the fringing has similar frequency or as the molecular features for the two spectral resolutions. So I was curious, is this a general property of some sort, or is this a coincidence that we're encountering this issue at different spectral resolutions?
So it will really depend on the width of the cavity of the Fabry-Perot here, and it's actually pretty large, so it causes high frequency fringing here, and that's just pure unluck perhaps.
Thank you.